Okay, let's talk about the good stuff in Rust, this thing called ownership. So, ownership is important once we understand how memory works in Rust and in other languages. So typically you have two kinds of pieces of memory. You have the stack and you have the heap. The stack is a place in memory where when a function is called, all of the parameters or arguments to that function are pushed into a piece of memory, almost into the scope of the function. So it's pushed into a piece of memory which is a box where anything that function does within its scope, it can make use of that piece of memory. When that function is complete, so when that function is executed, that memory is allocated, and it includes all the parameters and any of the local scoped stuff, space for those things, and that function executes and it can modify those things as it goes. And when that function exits, when it's complete, that entire piece of memory just gets removed off of the stack, and then you're back down to the lower function, the function that called you, and it continues in its thing. So as functions are called, as they're pushed onto the stack and they're resolved, they're popped off of the stack. So you can imagine that function calls are like, it's just really a stack, and that is physically how it works. So that's what the stack is. Stack is a very fast piece of memory. However, it has this limitation that it needs to be a fixed size. So the compiler needs to, during compilation, determine the size of the stack for a particular function call. So as it's compiling a function, it goes, okay, how big does the stack need to be? How many parameters, how many arguments are provided to this function? How big are those arguments? How much stuff is in local scope of this function? What are those types? How big are they? And it adds them all together, and it creates a stack. It's called a stack frame that is big enough to hold all of the variables in the scope of that function. And so it's weird to think of it like that, but it is a fixed size object. It absolutely is fixed size. So the question is, well, then how do you do dynamically sized things? What about if one of those parameters or one of those arguments is a string, and we don't know how long that string might be? Maybe we're fetching the string out of a file or something like that, and that file could be 1 meg, or it could be 100k or 1k or whatever, right? It could be a variable sized thing. So how does a function that needs to accept this string, how does it work? So the answer is that you have another kind of memory. You have this thing called the heap, and what the heap is a place where you can allocate dynamically sized blocks of memory that can be referred to by variables inside the stack, if that makes sense. And that's really what a pointer actually is. A pointer is something that lives in the stack, but it points to an address in memory in the heap, if that makes sense. And so effectively pointers are fixed size things. They're just an address, so we know exactly how big they are, so that means we can push pointers into the stack. But of course those addresses that they point to could point to a place in the heap. And so allocating, and so when you want to use the heap, you have to explicitly allocate the heap to a certain size, and when you want to free it, you need to explicitly free it. And so the stack is very simple actually, and the stack it really has no memory problems whatsoever, because as you're running functions, the stack gets created, and as that function exits, that entire stack frame is destroyed. So there's no possibility of leaking memory in this stack thing, because everything is fixed sized. It's very simple to manage. The difficulty comes in when you're trying to manage things that are on the heap, the dynamically sized stuff. So when we talk about Rust and ownership and memory, and this is true of C as well, we need to be explicit that we're talking about managing memory on the heap, really, not memory on the stack. The stack is very simple. So we talked about this a little earlier in the intro, but so managing this heap thing is interesting. And in the past, there have been two approaches. The first one is manually manage that heap. So be explicit when you allocate memory to the heap, returning a pointer, and be explicit to be explicit about when exactly that pointer will be released, or the memory that that pointer points to will be released. And in C, you would have had functions like malloc to allocate a certain amount of memory, and free to free that memory. And you would have to be explicit as a developer as to where that happens, where in the code that happens. And keep in mind that, of course, these pointers can be handed around. So I could malloc in function A, I could invoke then function B from function A and pass it that pointer, and have function B use that pointer, and maybe it calls function C and passes that pointer. And if C happens to be the last user of that piece of memory, I may choose as a developer to say, well, actually C frees that pointer. But then I would have to be careful to make sure that A and B, as we get back to them, as the stack returns to them, that they don't use that pointer anymore, because technically C has gone and freed it. And so that's kind of where the confusion and the difficulty of using something like C and managing that memory comes in. It's not entirely clear when you have a pointer who allocated it and who is responsible to free it. You could disconnect those two things. And you could say, actually, I will allocate it, and I assume that you will free it. For example, and that might be a valid pattern, absolutely, but you as a developer would have to be in charge of making sure that happens, because if that pointer went out of scope, i.e. the pointer was taken off of the stack, popped off of the stack, you would now no longer have a pointer that points to that piece of memory on the heap, and so effectively you would have no ability to ever free it again, nor even know about it. And that's really that is the fundamental basis of memory leaks, is that someone has allocated memory on the heap and they've forgotten about it. They no longer have a reference to it. And so that's a memory leak. The other memory model, which is an alternate and very popular in other mainstream languages, is having a garbage collector. So having a garbage collector be able to track heap allocations and know who had references to them. So the garbage collector would always kind of be in charge of allocating memory onto the heap. So it would always have this list of memory that had been allocated. And what it would do is it would be able to go and audit who exactly still has that address in their scope. And if they had that address in their scope, the garbage collector would be happy to not free that memory. As soon as it could find no one referring to that memory anymore, it would then mark it for freeing. And so that was always a process that would run kind of alongside your main runtime. So your program would run and you'd always have this attached sort of sidecard garbage collector who was always kind of checking your work to make sure that, always auditing to see what did you have, what do you have, what do you have. And as soon as it could see that you no longer had a reference to this piece of memory that it owned, it could then go and free it. So that is great because it frees you completely from having to manage the memory. But at the downside, that you have this extra process running inside your process, sort of cleaning up your work as you go along. And so, of course, there's a performance penalty to that. So programs typically written with manual memory management can generally outperform garbage collectors. But at the risk that they can screw it up and create memory leaks, and as well at the burden that the developer needs to really know what he's doing around allocating and freeing. So Rust, however, brings a third model called the ownership model. So let's talk through the rules that Rust has around ownership, and it is very much about enforcing particular rules. I think the first interesting thing is the owner, and there can only be one owner. Then there is the ability to, so there's something called moving. So we can move from owner to owner, move from owner to owner. The second one is we can, of course, copy. So create a new copy of the data and potentially assign it to a new owner, right? So and create a new owner. So almost creating a second owner of a copy of data. So that makes sense. Create a copy with a second owner, sure. You can borrow as well. And I think you can borrow mutably. Borrow mutably is the the fourth, right? And these are kinds of the rules. So the rules are that for a piece of data, you can only have one owner. You can, of course, copy that data, a second instance of it, and assign that to another owner. Owners can change, so you can move a piece of data from one owner to another owner, but as it moves from owner to owner, the previous owners become unusable. They're no longer usable. You can create borrowers of data, so I can have a piece of data that's owned by someone, and I can loan out access to that data, but the owner still remains the same, and there are rules around what those borrowers can do. So a borrower can really only read that data. It couldn't write to it. You can have multiple borrowers. You also, when you have multiple borrowers, or you have at least one borrower, you can't move the owner either during that time. And then borrowing mutably, it's similar. I think you can only have one mutable borrower of data. So borrowers, you can have multiple, and mutable borrowers, you can have only one. And we'll look through examples of these very quickly. So let's just create a new struct called A. So I'm just creating a new data type called A. It's like an empty record. It's like got no records. I suppose I could put something in here like it has an age of a U32 or something like that. That's fine. So it's just like a record structure. This will be something that will live on the heap, and so it's something that will fall under the rules of Rust's ownership model. So we can go let x equals a new A, create a new one. I'm just going to get rid of this age field to keep it simple. So that way we can just create a new one just like that. And so x at this point is the owner. I can assign it to someone else. So I can say, well, y now is the owner of A. So that you can imagine that there's this thing called A somewhere. X is currently the owner of it. X is the owner of it. Now at this point, y is the owner of it. And let's check if we can only have one owner. So let's say that z equals x as well. And at this point, you should receive a compile error saying use of moved value x. So it's saying that you can't, y is the new owner of x. X is actually at this point, completely unusable by anything. You cannot refer to x again past this point. As soon as the owner has shifted to y, x becomes unusable. The compiler will ensure that nothing you do after this line can ever refer to x again in any shape or form. And so this is immediately an issue. We could go equals y, and that would be fine. Now z becomes the new owner of y, and at this point y is at this point completely unusable by anything as well. So like that's a very simple example of moving of data just between some little variables. Of course this happens as well if we have a function. So let's have a function g. G takes a what do we call this thing, an a which is an a, and maybe it does something, maybe it does a print line hello from g or something. If we just look at the scope of this, when g gets called, the way you would read this is g, the function g takes ownership of a thing called a, well a I suppose, the a parameter takes ownership of the thing called a, big capital A, and literally at this point it comes into scope, and at this point a will be freed. Whatever it is. So the thing that a points to at this point will be freed, because there will, at that point, he will be an owner, and his ownership will run out of, he will fall out of scope, and Rust can know for certain that a can be freed at this point, because the ownership is not being transferred in this function at all. So G becomes almost like a little black box of A at this point. It goes in, it prints this thing, and whatever that A is has been freed and it's dead. So we could then call G with Z, no problem, and G eats the ownership of of A, and because it returns nothing, remember we talked about that unit thing, G doesn't return anything, so I can't really get anything out of this. It is just a unit. I can no longer ever refer to A again. I can never, I couldn't go let B equals Z or something. I can't do that because Z has transferred its ownership at exactly this point in time. So that's how memory moving works, very interestingly. So without this, A will be freed here. So if this is our example where we go x equals A, x transfers ownership to y, y transfers ownership to z, and in this particular code, Rust will free A down over here. The compiler has tracked the ownership of A through A to Y to Z, and it knows that Z goes out of scope right here, so it will free A, free that A object. If we call G, at that point, the compiler tracks the ownership of A through X, then Y, then Z, then into the function called G, meaning that A is now set to this little thing called A, which I should maybe call something else. I will call N. So it goes through to N, and then Rust knows to generate the free code right there. So A will be freed at the end of that function there, and no longer over here, because it is tracking the ownership. Yeah, so that's moving. That's moving of data structures, and that may feel weird and interesting, but it's just something that you get used to. So wherever you see things like this, you can see that ownership happens. So just because N takes an A, that is explicitly saying takes ownership of A. There is an alternate, which is the next. Okay, so let's talk about copies next. So of course you can also copy. So this doesn't have to be the case if it is data being copied, if that makes sense. So let's think of an example with a copy. So first of all, I think I want to make my structure copyable, and a simple macro we can use is derive. I think it's clone. I think we call derive clone, which then gives us the ability to go let y equals x dot clone there. So this is just a little macro that clone is a trait, and the Rust a macro called derive is able to automatically generate cloning functions for a lot of data structures, and because this one doesn't have anything complex in it, it can derive the clone function for a struct of A. I could go and implement it myself as well if we go and look at what clone looks like. Oh, it's a compiler built in. Okay, so maybe I can't. Anyway, I can derive clone. It's a very easy structure to copy. So at this point, so if we go and use clone, we now have actually kind of two A's. We have X pointing to the original A, and we have Y pointing to a clone of A. It's like a second A. Here is the first A, and here is the second A. And each of them have a distinct owner, right? So if I call G with X, the owner of the first A goes in here, and the first A will be freed down there. First A freed here because we passed it into G down there. But I could go let Z equals Y, and that should be totally fine. So now Y has moved into the owner. Its new owner is Z, which means that the second A will be freed over there, right, when Z goes out of scope. So isn't that interesting that we can make a copy using clone? So totally makes sense. We can copy the contents of that piece of memory. But of course, this is like we are now creating a whole separate piece of structure. But there's a common pattern that often you can end up just sort of cloning data because you do need physically multiple copies of it, and maybe multiple owners of it. So you would clone. So that makes sense. Obviously, I couldn't go X down here. That makes sense. So X, the compiler should pick up and say, no, you can't do that because X was moved here. And move occurs because X is type A, which does not. Consider changes. So I think actually, is this, if this is intentional? Oh no, it's just saying that's unused, yeah. But X is saying it was moved there. Moved, value was moved here on the G, which we know. Okay, so that's how moving works, and copying and moving. So we've done those two. So what is borrowing? Borrowing is also is kind of a, so you don't always need to take ownership of structures. Maybe you just want to read them and use them for a small amount of time, and you don't want to take ownership. So then you have a mechanism called borrowing, and the rules around borrowing are pretty simple. So let's make an A again. X is an A, and I want Y to be able to just borrow from X, and that is the syntax for borrowing it. We use this little ampersand, and it says actually Y has borrowed it from X in a way that X is still the original owner, and X can still choose to transfer ownership later, but we could have multiple copies of multiple borrowers as well. So that is totally valid. So we can have Y and Z are both borrowers of the same A, that A up there, and X remains the owner. So X can choose to later on transfer ownership to someone else like that. So that's still totally valid. At this point though, where the ownership is transferred, X is dead, so are the borrowers. And in fact, I think if we even choose to use a borrower down here, let A equals Y, like try and touch Y, I think, yeah, we are actually prevented from shifting ownership. The compiler is actually saying, hey, like your borrowers do stuff later, so I'm not going to allow you to move your ownership up here. So kind of the rule is you can have multiple borrowers, but you can't transfer ownership whilst you have any. So whilst you have any borrowers, you can't transfer ownership either, if that makes sense. So whereas it would be fine like that, if that makes sense. So that's kind of the rule for borrowers, is they have a read-only view. Functions can also be borrowers, and that's actually a very good pattern, is functions. Sorry, let me remove some of these comments, they may be confusing. Functions can also borrow. So when G is called, N becomes a borrower of an A, and they follow the same format. So when I call G with X, I lend it, I suppose, to G over there, which means the freeing still happens down here. Freeing of A happens here, where X, the owner, goes out of scope, right? So no ownership is being transferred in any of these. We are just borrowing that value. And when you borrow it, you can read from it. You cannot write to it. I don't think you can ever get a mutable. You can't convert a borrowed reference into ownership, and you can't convert a borrowed reference into a mutable reference either. I don't think. Maybe that's worth maybe trying. I'm not sure. I'm not 100% sure. So, and then I think the last one is a mutable borrow, and this I actually hardly ever do, so I might get it wrong. Let's see how it works. I think, do I go mutable borrow of X? What if the second is, maybe my syntax is wrong here. Cannot borrow. X is mutable, is not declared as mutable. Oh, okay. So X itself needs to be a mutable owner. It is a mutable owner, and so therefore I can get a reference. A Y can be a reference to that mutable reference to that same object. But I don't think I can have a second one. I don't think I can, or maybe I can, but then I can't do stuff with it. What would I do with it? Why? Is that valid? No. Let's see what the error is. Cannot borrow X is mutable more than once at a time. The second mutable borrow occurs here. Yeah, exactly. Because so previously, if this thing was not mutable, this would be valid. Is that it's okay that I can have a second borrower and I can use the first one. It's fine. But as soon as I have a mutable one, it kind of follows the same sort of moving laws, that it won't. So as soon as the second mutable borrow occurs, all previous mutable borrows are unusable. They become unusable. So it's almost like ownership, except it isn't ownership, because their scope could be, when they go out of scope, the original object is not destroyed. I suppose that something like that. Yeah. So those are the laws of memory management. It is very similar, I suppose, in some respects to the way you would write code with C. You would still be kind of thinking about where does memory get allocated and where does it get freed. But the compiler is going to check your work as you go and make sure that there's never a scenario where you are using something that has already been freed or that you are failing to free something that should be freed. The compiler is checking that through these kind of sort of very simple mechanisms, actually, of moving data to new owners, allowing you to make copies of it, that's fine, allowing you to borrow multiple or declare multiple borrowers of that data, but in order to only read it, and then have one mutable reference, one borrowed mutable reference to it at any stage as well. And by enforcing these rules, you actually end up with almost guaranteed safety around memory, which is very interesting.